Colton, as folks come in, could you give them an exam?
Yeah.
In that scores are confidential, so don't like flash them around.
Yeah.
Okay. No, what's your name, sir?
Okay.
Sorry?
We are live. And this is the slide you want to start off with?
What?
This is the slide you want to start off with?
Josh Groban?
Yeah.
Yeah. Okay, Colton, exams are right there.
Okay.
What's your name, sir?
Josh Crossgrove.
Josh Groban. Thanks.
find out how I did on modern physics.
Oh,
Okay.
I hope so too.
It's kind of a cool class, actually.
Yeah.
Yeah, it's like an introduction class almost. To, like intro to quantum physics.
Okay. Awesome.
Just, it doesn't like go delve really deep into it.
Yeah.
It's still pretty cool.
Nice. Yeah, I started reading about quantum physics and decided, no, we'll just stick a little bit bigger. Go nuclear engineering. It's neat.
Yeah, luckily right now it's more qualitative than
Okay.
quantitative.
Good.
So it kind of gets you that foundation.
Yeah.
Advanced wire. It's like, oh yeah, this isn't so bad, but it's like, yeah, it is.
You fool.
Okay, good morning, folks. It's about that time. Got the exams all graded. For those of you who are in class and you got it back, what's posted is the number of points, not your actual score. Scores and grades are posted on Moodle. I did curve the exam. Before curving, the mean score was a C minus, and there were only 4 A's. So I curved it so that the mean would be a B minus, like our first exam. And that meant that we had, something like 8 B's, 8 A's. Darn it, I just posted this last night. Something like 8 A's, 14 B's or so, and 8 C's. I can't remember. It says posted. I posted it online. Sorry for me forgetting that. I didn't actually write it down here. So if you can pick up the exam in class this week, after this week, you could pick it up from the main physics office. I'll have them down there. Also, we have upcoming this Friday and a week from today, the electricity activities that require significant amounts of equipment. And so please respond to the email I sent out this morning to let me know if you anticipate not being able to attend in person in the classroom on either Friday or Monday, so that we can make other arrangements. And whether arrangements are necessary will be determined by how many people we'll have to make special accommodations for. So please do respond to that email if you do not anticipate being in class on those 2 days. Okay, so I'd like to start off with a question on the Doppler effect. Remember, we had that demonstration with the Doppler rocket, that little Nerf ball on Friday? And that if basically, well, if a source of sound is either approaching you or receding from you, relative to you, you'll hear either a higher pitch or a lower pitch, because the sound waves will be reaching you more frequently or less frequently. And so, recalling that discussion from last Friday, consider this question. You've got Josh Groban going down the highway, getting carried away, singing along, and didn't realize he was speeding. So he's going 80 miles an hour and singing a steady high C, which Josh Groban could do. Okay, a highway patrolman is coming up from behind at a speed of 110 miles an hour, blaring this siren, which for some odd reason is right around an E flat. So, 4 possibilities here, or at least 4 statements, which is correct. Josh hears the siren at a lower frequency than a high E flat, and the patrolman hears Josh at a frequency lower than a high C. Or Josh hears a siren at a lower frequency while the patrolman hears Josh at a higher frequency. Or C, Josh hears the siren at a higher frequency and patrolman hears Josh at a lower frequency. Or D, they both hear each other at a higher frequency than what they would have heard if they were stationary relative to them. So think about this for a bit, please. And get cards ready when you've got an idea. So both lower, one higher, one lower, the other higher, lower, or both higher. That's what we're looking at here. Okay, show me your cards. Okay, what's it look like on chat?
1D, everyone else, oh, one's D, 1A, and the rest are C's.
Okay, so C's and a D and an A.
Yes.
Okay, can I get a volunteer to defend A, please? Anyone for A? Okay, how about C? Can someone defend C? Mr. Horsley?
So what I came up with or figured was Josh Groban is going slower than the patrolman. Because the patrolman's coming in faster on Josh Groban than
Can we move that chat so we can read? Sorry, continue.
whereas they're coming in faster on Josh Groban, and with the patrolman, those ways are kind of different.
Okay, so clearly the source of the siren is getting closer and closer to Josh. So he would hear that at a higher frequency. But you're saying that the patrolman would hear a lower frequency for some other reason?
Yeah.
Okay. Can I get a volunteer to defend D, please? Anyone online? Mr. Anderson?
So the reason I picked D was because they're both getting closer to one another, which means that the waves are going to be being perceived more rapidly.
Okay, so you agree with Mr. Horsley about what what Josh would hear, but you would argue that D is correct.
Because he's also getting closer.
Okay, and that the patrolman is also getting closer to Josh, and so he would be hearing the waves coming in more frequently. So that would mean both would hear a higher frequency.
Right.
Okay. Does anyone have anything to add to either of those points? Okay, I'm going to just say that A and B are not correct, and it's either C or D. Let's have some discussion about what could be going on.
Well, you guys have heard my argument.
So I can definitely see how one thing I kind of agree with it. If I'm north being higher than usual, each other.
Anything showing up on chat?
Oh, we just got one.
Any comments? Please.
D makes more sense now. Both vehicles are getting closer to each other, so they both should hear a higher frequency.
Anything else? No.
They are both getting closer to each other, so they will both receive each other's frequency at a higher rate.
Okay, so we've had some exchanges. Show me your cards. What are you thinking now? C or D? What's it look on the chat?
So
Oh,
far,
geez.
yeah.
So far.
What?
All D's so far.
All Ds? Okay, that's good enough. Yes, D is the correct answer here. It's pretty much all relative. If you're getting closer to a source of sound, you're going to be intercepting those waves more frequently. And if you're going away from a source of sound, you're going to hear them less frequently. That's pretty much what the Doppler effect is involved. So if two people moving the same direction, yet their relative position is getting close to each other, they're both going to hear a higher frequency. If they're clearly moving in opposite directions, they're both going to hear a lower frequency. In fact, the only situation where you could possibly hear one hearing a higher frequency, the other a lower frequency, would be as if you're like in a very strong wind, but the wind speed is actually on the order of the speed of sound, enough to shift it for motion. But I didn't talk about anything about a third complication, which could be whether or not there's a wind going. And that if there's a strong breeze, that will also, because the wave travels in air, and if the air is physically moving, that could give you a Doppler effect as well. But we did not talk about that complication. But in general, if two things are getting closer, they're both going to hear a higher frequency relative to each other. And if they're both relatively getting farther apart, they're both going to hear a lower frequency. Okay, let's hit to the next slide. So, Mickey Mouse, so named to avoid copyright infringement. He wants to get the steel ball up and out of the bowl, but he's not strong enough to actually push it out by all at once. Meaning he's not strong enough to get it all the way to the rim by just trying to push it up the side. So, is there a way he could get it up and out of the bowl? And this is obviously a very, very smart mouse, because he's not going to be able to eat steel. Why would he want this steel ball? Very strange. So really, C is just there as a joke. Basically, can he get it up and out, or can he not get it up the side of the bowl and out? Is there some way that he could do this? And if so, maybe pose an idea of how he could possibly do this. How he could get the steel ball up and out. I want kind of a quick turnaround on this one, so just give me your impressions. Go ahead and hold up your cards. Yes or no? What's it look like on mine?
A little bit more B's than A's, but it's about the same.
Okay. Could I get a volunteer to defend why he could not possibly get the ball out of the bowl? Anyone want to say anything about that point? Okay, how about B? That there is a way that he can get it out. Can somebody want to defend that, maybe outline a possible attack?
I can try. So I was thinking that the mouse could still use like its momentum to try and gain speed, enough speed to get over the ledge of the bowl, because as you push it up one side of the bowl, it's obviously going to roll back down, and if you keep adding a little bit more like push to it, kind of like a merry-go-round, where as it like you start pushing it, it'll just keep going, and it'll start gaining momentum as you just keep pushing.
Okay, so basically push it a little bit each time it rolls by, and eventually it'll roll up and out, kind of like a kid on a swing.
Yeah.
Okay. Anyone want to defend why this, why he couldn't get it up and out, maybe why that procedure wouldn't work? Okay, I'm going to go for a long shot and think that Ms. Wheatley was so very convincing that nobody is going to answer A at all, because B, in fact, is correct for exactly the reason that Ms. Wheatley said, in that basically this is the whole idea behind resonance. A small periodic influence can often lead to a larger and larger vibration of a system. I spent quite a bit of time on Friday talking about that. And that has a lot to do with music as well. Why musical instruments work and how we can make sounds with many devices. So, going back to the spring, let's see, Mr. Fisher, could you help me out?
Yeah.
So, got the spring here, and actually, no, I don't want to do this just yet. I want to do, I just saw this. I want to do this. So, I got these resonance boxes, mentioned these before, in that these are loud, much louder than normal tuning fork because the vibration of the tuning fork vibrates the box and therefore vibrates the air in the box. So this is an example of a resonant situation. And I've got these two boxes set at the same frequency. But something that's rather interesting in music is that if you have two sources of sound that are just a little bit off in frequency, say they're oscillating really close to the same frequency, but then one might have a bit faster oscillation, well, they'll get out of phase, we call it. They will no longer act constructively, but then a little bit later, they'll act constructively again. And so we'll get a time when they're going to be adding their sound together and then canceling each other and then adding their sound together again later, as long as the frequencies are close. And you can hear that if I move the weight on this time up a little bit, increasing its inertia, so its oscillation is going to be slower. So by raising this weight, I made the frequency of this one a little bit lower. Do you hear a kind of a wow, wow, wow sound? That's where they're adding together constructively, and then when it gets softer, it's when they're destructively adding, and then they act constructively again. So you get this when things are close in pitch, but off just a little bit. And this is also very important in music. In fact, when you go to a concert where you have like a symphony, you'll often hear them warming up their instruments, and you'll sometimes hear a violin. Everybody's quiet, and the violin, plays a note, and then other people will chime in trying to play a similar note. What they're doing is they're trying to tune their instruments so that they're all at the same frequency for that note. And they're listening for beats. Musicians out there, you probably know that this is how you tune an instrument. You play a steady tone, you play your instrument, and you try to adjust like the tension of the string, adjust the position of a slide of the brass instrument, or adjust the positioning of the headpiece if it's like a flute or a clarinet. So what they're doing is they're basically trying to change their frequency of their instrument so they don't hear any beats. Because if you don't hear any beats, that means your frequencies are really, really close. You're not going to be able to turn it perfectly, but what they do is they basically play the longest sustained note that they anticipate having to play in that piece. And if they cannot hear a distinct variation in this, how the sounds combine, they're good enough. Piano tuners will sound basically a tuning fork and then play the note on the piano, and they'll listen very carefully. And the best piano tuners, the most expensive ones, will take hours to tune a piano because they'll sit there and listen for minutes at each note to try to listen for a beat. And if they can't hear a single period of this beating, they consider it good enough. And so a very important principle in music. Okay, Colton, I'd like to go back to the spring now. Where did the spring go?
It's on your left.
Ah, there it is. It's hanging from me.
So my younger brother, the trick with the standing wave, and he thought that was pretty cool.
Okay, so we don't need much here. So we can also get resonance here by applying an influence at the natural frequency of the spring. We can get large amplitudes of oscillation. And how frequent the oscillation is what we associate with pitch. So a slow oscillation, let's do it like here. So to make the string really, really loose. So this is like a slow oscillation. So it's like a low note, low. If I make it really tight, we increase the restoring force, increase the acceleration, and we'll have, try to hold that still. We have a higher pitch. This is like a higher note. Wah! Okay? And we can get that faster oscillation with either a tighter spring or a really short spring. And in most instruments, the loudest note you hear is the fundamental. basically, in this case, where we have a wavelength between us, this is like with a stringed instrument. But you will also get what are called the harmonics. You'll get the second harmonic, sometimes called the first overtone, where now we have a wavelength between us, if this is like a stringed instrument. Or faster. Yeah. Here's the third harmonic with the second overtone. You can go on from there. Basically, fast oscillations are high pitches. Oh, here, go do it again.
Do it again.
So, but the amplitude is what determines the loudness. So here's like a soft sound, like a la, la. Okay, let's be trying to sing the same note but louder. Okay, I don't think I succeeded. I think my frequency shifted. That's not big fast enough. Okay, you get the idea. Big oscillations, loud. Small oscillations, soft. More frequent oscillations, higher pitch. Slower oscillations, lower pitch. So that's kind of how it goes. But we can distinguish a clarinet from a trumpet, from a flute, even when they're playing the same note. Basically, when the fundamental frequency is the same, they get the same note. But you can clearly tell them apart because of the relative amplitude of these harmonics. For example, let's go ahead and have that Audioscope program up. So Brendan's got a program here that we're going to shift to that will display either the sound intensity as a function of time or break it down for frequency, right? Let's do it as just the amplitude.
Okay, hold on. Something's goofy with screen share.
Okay, so I don't want the frequency display. I want the waveform. Okay, so what we're looking at here is basically what the microphone is detecting as a function of time. And you can see kind of like a wave behavior for my voice. Well, let's play a pure tone. So the scale here is on the order of hundreds, is that hundreds of milliseconds?
Looks to be 11.6 milliseconds.
Okay, so on the order of 10 milliseconds. And it looks like a sine wave. Let's hit something that's an octave lower, basically half the frequency. That's not really showing up well, is it?
There a bit.
Yeah, we're going to see like one wavelength across here. Okay, I guess that did show up okay, just kind of faint. And I'm going to embarrass myself and try to make a sound out of a flute. And I was going to play a middle C just like that same note, but I can't because the two keys are like off. So I get, that was a little bit higher than middle C. Let's switch the frequency display. So what we're seeing here is we're seeing frequency as a function of amplitude. And so it goes from 0 hertz to what is that? 22,000 hertz?
Yeah.
Is there any way to change that scale?
Not that I'm aware of.
Okay. So we see some spikes showing up. And if this is a pure tone, we should only see like one spike. Let's play the tuning fork and see what that looks like. Okay, it's looking like a peak here is from our ventilation system. We need to look for a peak right around here. If you can move the cursor to where I was pointing.
Yeah.
So folks online can see. Right around here is where about 256 hertz should be. That's what a mil-C is. That should be.
At the bottom, it shows you what the cursor is at.
Okay. Oh, that's very useful. So right around 256 is where we should hear. Yeah, 256 hertz. Yeah, right there, that's peak. Okay. Yeah, I wish we had more of a scale to the side so that would be clear. This is really going to much higher frequencies than what I'd like. Okay, but if I play a trumpet, actually this is a cornet. It looks really messy. Yeah, I don't think I like this program as well. It's not as clear. Switch to the time scale. So you should see, is there a way to change it so you can see more up on this, or?
Not that I'm aware of in the 30 seconds I played with it.
Okay. But you saw we have a regular pattern, and the overall period of that pattern was the same as what we had for the tuning fork. But there were a couple of extra bumps. It wasn't quite a pure sine wave. It looked fairly complicated. That's because of the harmonics that are present in the trumpet. We call this the recipe of sound, in that any given instrument, even individual voices, will have like a fingerprint in sound of these harmonics that are present. And so that's why you can recognize a clarinet from a flute, because the waveforms are basically looking different. You've got the main frequency, but you'll have, on addition to that, less loud contributions from other harmonics that give everything a very characteristic tone to it, a sound to it. And so you could recognize the voice of your mother or father, even in a crowd, because you know what sort of frequency contribution. You recognize their voice. Everybody's voice sounds just a little bit different because of slight differences in the harmonics that are present. So this is how we can tell different instruments apart and also recognize different voices as well. There's something else that's, let's see, rather interesting about our ears, in that our ears are not linear instruments, in that something is loud to us if there is more energy in the sound wave, if the amplitudes of the oscillations are greater. And we can measure the intensity of a sound wave in watts per square meter, basically power per area that it's hitting. And the human ear is actually surprisingly sensitive to a wide range of frequencies. We don't have the best, well, a lot of other animals hear a lot better than we do, but our range of hearing is actually not too bad. There are some animals that have a wider range of hearing, but not that many. So our hearing isn't as good, but at least our range is pretty decent. And our ears are not linear. Basically, for something to sound twice as loud to us, the intensity, basically the energy of that wave per square meter has to be about 9 times greater for us to perceive it being twice as loud. And that's one reason why we have such a wide range of hearing is because, well, actually, no, it's not from frequency, but at least from loudness. And because of this fact, we don't measure sound intensity as much as we measure what's called sound intensity level, which is basically goes as the logarithm of the actual intensity. And the faintest sound we can hear is around 10 to the minus 12 watts per square meter. That's the intensity about the faintest sound we can hear. And we basically call that a sound intensity level of 0 decibels. So 0 decibels doesn't mean there's 0 sound. It means that's the faintest sound we can possibly hear. And a factor of 10 in intensity greater is then 10 decibels. And a factor of 100 in intensity greater is then 20 decibels. So each change of 10 decibels is an increase by a factor of basically 100 in intensity. So if you go up by 1 decibel, that's like going up by a factor of 10 in sound intensity. And the reason for doing it in factors of 10 is because the logarithm base 10 is pretty easy. It actually would be more precise and more aligned to our hearing if it went up by the logarithm base 9 instead of the logarithm base 10. Because something sounds twice as loud to us if it's 9 times more intense, not 10 times more intense. But one other insidious thing is that the intensity level where we start to hear pain is around 140 decibels. Actually, it's between 120 and 140. It varies person to person. But the damage threshold, where you actually get permanent hearing loss, can range from 100 to 120 decibels. So basically, you could be listening to sound that you know is loud, but it's not painful, yet you're still doing permanent damage to your hearing. And so that's the danger of playing loud music, is you can be permanently damaging your hearing without realizing it. It's not to the pain level yet. If you're to the pain level, you should be darn sure that you're actually causing physical damage to your hearing. So I do a lot of work with kids, and I have done for several decades, where I go to schools and I have activities with kids. And I've noticed over the last 30 years where I've been basically a professor, and 40 years what I've been since I've been involved in education, folks' hearing have gotten a bit worse as far as younger kids go. And I think it's having to do with the prevalence of louder music, especially with little headphones that folks are more likely to wear. So be cautious, and if you have kids or when you have kids, do caution them about listening to loud music, because it could be causing damage even without it being to the level that we consider painful yet. So let's go with the next PowerPoint slide, if we could, please. Speaking of children, given that sound intensity falls off as 1 over r squared, we have a lot of things that fall off as 1 over r squared. Gravity falls off as 1 over r squared. The electric force does, and also the intensity of sound does, because the surface area of the sphere is proportional to the radius squared. And so if the energy is distributed over the surface of the expanding sphere, the bigger the sphere, well, the more area that's spread out over, and the intensity, which is basically energy per time per area, drops. So that's why we have it falling off as 1 over r squared. So given that intensity falls off as 1 over r squared, how far should you move from a screaming child so that it is only half as loud to your ears? Should you increase your distance by half? Should you double your distance? Should you triple your distance? Or approximately quadruple your distance? That's the question. How far away do you have to move for something to sound half as loud? So get your cards ready. Oh, what sphere am I talking about?
Yeah.
Basically, it's any sphere. The area of a sphere goes as 4 pi r squared. That's the surface area of a sphere. And so if you have a source of sound and you're talking about intensity being energy per time per area, as the sound wave moves out, that energy is spread out over an expanding sphere. That energy is over a larger and larger area as the sound propagates. And since the area of the sphere goes as 1 over r squared, so does the intensity. Was there another chat question?
No, that was it.
Okay. So show me your cards.
All A's so far and 1 B.
2 B's.
So we have A's, do we have B's?
We have 2.
Do we have C's?
No.
Do we have D's?
No.
Yeah, we have D's here.
Or B's here.
Any D's on chat though? Okay.
You have a question though. How are A and B different from each other?
Oh, say if you're 10 feet away, A would mean moving 15 feet away. B would mean moving 20 feet away. By increasing your distance by 50% means whatever distance you have, increase that by half. So that would be from 10 feet to 15 feet. And B would be from 10 feet to 20 feet. C would be from 10 feet to 30 feet. And D would be 10 feet to 40 feet. Just to give us explicit example of what it means to double or triple your distance. Can I get a volunteer to defend A, that you should increase your distance by 50%? Anyone for online? Mr. Anderson?
I was just kind of doing the math for this. So you gave the example of being 10 feet away and adding an additional 5 feet of distance. Well, since it's squared, like you said, then that would mean the sound reduction would go from being 10 squared to 15 squared. Which I haven't done the actual math on, but I think that's about enough to double it. And since if you double it with this thing of squaring it, if you double your distance, that actually quadruples the sound reduction.
Okay, so a doubling of the distance would, if you go by the 1 over r squared, that would quadruple the intensity if you increased by a factor of 2? Or would it decrease by a factor of 4?
It would decrease by a factor of
So it'd be
4.
quartered if you double your distance.
Exactly.
Okay. So since we don't need to quarter the intensity, that's why you went for A.
But
Since you don't need to quarter your intensity, you only need to reduce by half. That's why you went with A, because it's the closest.
Yeah.
Could I get a volunteer to defend B, that we should in fact double the distance? Anyone want to defend B? We had quite a few folks choose B, didn't we?
We had a couple,
Couple?
2 or 3.
Did anyone choose C?
No C.
Okay, could I get a volunteer to defend D? Anyone for D? Okay, I really don't think discussion here is needed, because I'm not getting anyone defending the right answer. For a baby to sound half as loud, say if it's screaming, do you just say you're 10 feet away from a screaming child? Will moving to 15 feet really make much of a difference in your own experience? No, it won't. We're not talking about, by having it half as loud, we're not talking about having the intensity as half the value. In order for something to sound half as loud to us, what must we do to the intensity? Anyone? For a human being, for something to sound half as loud, the intensity must be less by a factor of 9. I said that earlier. That's why we use a decibel system for a sound intensity level, because we are not sensitive to intensity. You have to basically have the intensity increased by almost a factor of 10 before we perceive it to be twice as loud. So you've got to reduce the intensity by a factor of 9 in order for something to sound half as loud to you. And in order to have the intensity fall off by a factor of 1/9, you've got to triple the distance. By tripling the distance, 1/r² is then 1/9. So if it's to make it sound, so you're 10 feet away from a screaming child, if you want it to sound half as loud, you're going to have to move 30 feet away, triple your distance from that kid. Does that sound more like something akin to your own experience? Yes, the reason for that is because our ears are nonlinear instruments. Doubling the intensity is barely a perceptible change in loudness to us. You have to increase the intensity by a factor of 9 for it to sound twice as loud, and you have to decrease it by a factor of 9 for it to sound half as loud. So the correct answer here is C. You've got to triple your distance. Is that sensible to folks? Okay, and it should be closer to match what your personal experience is. Okay. There's something else that sound tends to do, is it tends to, well, let's see. I could probably do another quick demonstration with interference. You know how sound adds together? I had the little wavy strips out. Then you have two sources of sound from 2 points. If they add up just right, the sound intensity can add. The intensity can add. It'll sound louder, but a little bit off to the side, the sound waves might cancel. If they're giving you the exact same tone and they're exactly in phase, you'll hear loud spots and soft spots. And that's why in concerts, they like to spread the speakers out so you don't get that. I'm going to bring out this rod again and set up the longitudinal waves. So basically each end is where we have the ends vibrating. And so what's producing the sound is this end pushing the air and then this end pushing the air. So I've got two sources of sound that are going to be in phase and separated. And this is not going to work for anybody remote. So this is really only a demonstration for people in the room. In that as I then move where those two sources of sound are, well, the distance from you to each end is going to change slightly. And what I want you to do is cover one of your ears. Basically plug up one of your ears and try to hear if you hear a change in sound intensity as I move the two sources. That'll indicate that you have some interference going on with these two sources of sound. Is that perceptible? We hear it's like louder, softer, louder, softer, louder, softer. It's very noticeable to me because I'm really close to it. In the back of the room, were you able to hear that? Okay, a little bit. Okay. So one other thing that I'd like to share with you is why we put speakers in boxes. And I presume you were thinking I'd be using my phone?
Yeah.
Okay. So dang it, where's my? Yeah, here it is. Google Play Music is no longer available? What? Okay, do you get music on your phone real fast?
Yeah.
So I can't play all the music that's on my phone?
I think they moved to a different app.
Yeah, they did. That sucks. I didn't notice. Okay. So I've got here a speaker. Basically, it's a membrane that vibrates. And as it's pushing sound one direction, it's pulling sound the other direction. So basically, when it's pulling back, it's pushing air this way. And so it's really creating two sound waves, one that moves forward, one that moves backwards. And they're out of phase with each other. Where I'm creating basically a crest in front of it, I'm creating a rarefaction or a trough behind it. So go ahead and just play some music. What?
I had it on.
Hear that? Okay, that might not be the best sound quality because it's a bare speaker, but I can improve it greatly by making that sound. You have the difference? And to be clear, I'm not actually touching the box. The box is, or the board is not vibrating. Okay, that's good. I don't know if that's showing up well on the microphone for those of you remote, but sound also spreads out. So you've got something pushing sound this way, pushing the air this way and getting a sound vibration. Well, sound spreads out, it diffracts. Basically, the air out here is pushing the air in front of it, but also pushing kind of air to the side. So the sound will spread out and around. And the wave that the speaker is sending forwards is exactly out of phase to the wave that's going backwards. And the two would normally cancel. By putting a box in front of there, we limit slightly the amount of sound that's going back here that can curl around and interfere with the sound that's going forwards. To do an even better job, we put this thing in a box so we completely eliminate the sound wave that would interfere with the sound wave going forward. So that's why speakers are put in boxes. Is not to have the thing resonate to make the sound louder, but to eliminate completely half of the sound wave so you don't have the interference going on. It's because of this diffraction effect. So somebody's around a corner from you and talking, you can still hear them because the sound bends. They might not be as loud, but you can still hear them. And this subtraction, this interference is pretty perceptible. And that's why you put speakers in boxes. And the amount of diffraction you get, the amount of spreading out, depends on frequency and the aperture. Have you noticed that a small, on the old speakers, you had the tweeters that were very, very small, the mid-range, which is about mid-sized speakers, and then the woofers were really, really big? That's because you get less diffraction with the higher frequencies. But you get more diffraction if you make the opening really small. So by making the tweeter small, they force it to spread out more than it normally would. And by having the woofers really, really big, they make it so it doesn't spread out as much to get the same sort of sound coverage for each sound range. So that's kind of just inside, but that's all the time we have.